How does a skyscraper weighing hundreds of thousands of tons stand securely on ground that can shift, settle, or conceal hidden weaknesses? The answer is not found solely in steel and concrete. Before a single beam is set, engineers scrutinize soil reports, water levels, and rock layers, each detail holding clues about the ground's true character. Miss one clue, and a bridge could crack or a skyscraper could tilt, with consequences that unfold long after construction. This video examines the investigative process behind these critical decisions, focusing on the specialized toolkit geotechnical engineers use to interpret the ground's silent warnings and establish a foundation for lasting stability. So, what is geotechnical data, and why does it matter? Geotechnical data is the deep, often overlooked layer of information that comes from beneath the surface of a construction site. It includes everything from soil composition and groundwater levels to the characteristics of underlying rock formations. Far from being a routine technical step, this data forms the groundwork, quite literally, of every sound engineering decision. Understanding what lies beneath isn't just a matter of good practice, it's a matter of engineering integrity. When collected systematically, analyzed with precision, and interpreted through experience, geotechnical insights become essential tools for anticipating risks, guiding foundation design, and ensuring long-term structural performance. Reliable geotechnical insights allow engineers to flag hidden dangers early, such as zones prone to soil expansion, settlement, or seismic instability. They inform the most suitable foundation types by clarifying how much weight the ground can support and how it might behave under changing conditions. And critically, they help prevent costly surprises during construction by reducing the chances of unexpected site conditions, forcing major last-minute changes. Beneath every construction site lies a record of past events, layers of soil and rock shaped by centuries of geological activity. This subsurface material holds the critical clues engineers need to assess risk and design safe foundations. Identifying and interpreting these clues is essential, as the ground's history may reveal hidden threats. Zones prone to liquefaction during earthquakes, or expansive clays that swell and shrink with seasonal moisture changes. Overlooking such risks can lead to costly damage or even structural failure. To uncover what lies beneath, geotechnical engineers rely on focused investigative methods. Soil boring is a primary technique, using augers to extract cylindrical samples that preserve the sequence and characteristics of subsurface layers. These cores are tested in laboratories to determine key properties such as shear strength and compressibility, critical data for evaluating bearing capacity, settlement potential, and foundation design. For instance, knowing how compressible a clay layer is helps predict building settlement over time, while shear strength informs slope stability and safety assessments. Another widely used method is the cone penetration test, CPT, in which a steel cone equipped with sensors is pushed into the soil at a constant rate. Though it doesn't recover physical samples, CPT provides a continuous profile of soil resistance and friction with depth, helping identify weak zones or layers susceptible to water infiltration. This data informs foundation depth, pile selection, and whether soil improvement is necessary. On environmentally sensitive sites, non-invasive geophysical techniques such as seismic surveys offer valuable insights with minimal disturbance. By using energy waves to map subsurface conditions, seismic surveys help locate bedrock, detect faults, and identify anomalies across wide areas. Once the field data is collected, laboratory tests translate the physical samples into actionable numbers. Shear strength tests quantify the soil's capacity to resist sliding forces, guiding the choice of retaining structures and slope angles. Consolidation tests estimate how much soil will compress under load, guiding decisions on settlement control and ground improvement. Permeability tests reveal how easily water flows through the soil, informing drainage design. At AXA Engineers, this evidence-based geotechnical approach is standard practice. With over 15 years of collaboration with U.S. civil engineering firms, AXA's dual team model ensures investigations are carried out with both technical rigor and deep project context. Their engineers are immersed in client workflows, combining field results, lab data, and advanced modeling tools to produce clear, risk-informed recommendations. Understanding the ground is only the first step. The next challenge lies in translating that understanding into practical, reliable design, especially when teams are dispersed across continents and time zones. AXA's integrated, globally coordinated workflow ensures that this crucial transition is seamless, accurate, and aligned with the project's broader goals. Possessing geotechnical data is only one part of the engineering process. Ensuring its accuracy and interpreting it correctly, especially across continents, is a far more complex challenge. Field data such as cone penetration test results or boring logs are isolated clues. The real engineering value lies in analyzing these clues and converting them into actionable recommendations that shape foundation design. Certainty is not inherent in the data. It must be built through rigorous interpretation. In global design outsourcing, this challenge is magnified. Geographic and cultural distances can lead to misinterpretation of local geological nuances, particularly if engineers are unfamiliar with regional soil behavior. Time zone gaps can delay communication, and data quality may suffer when teams use different software tools or adhere to slightly different standards. To manage these risks, AXA Engineers has implemented a robust quality management system supported by a dual-team working model. This approach bridges geographic divides by forming an integrated project unit aligned with U.S. working hours. A U.S.-based project management team collaborates in real time with the technical design team, ensuring immediate client feedback and seamless communication. This model goes beyond simple file sharing or scheduled video calls. It enables a collaborative workflow where data interpretation or scope concerns can be identified and addressed early. This operational structure is central to AXA's ability to deliver consistent, high-quality engineering outcomes across borders. A cornerstone of AXA's methodology is immersive training and on-site experience. The company sends key engineers to client facilities in the U.S. for extended assignments. These engineers do not just review technical codes. They work side by side with client teams, absorbing design philosophies, communication practices, and project expectations. This hands-on immersion equips them with a clear understanding of both explicit requirements and the often unspoken local context that shapes engineering decisions. Their work reflects not only ASTM or AASHTO standards, but also the specific site conditions and client expectations. This alignment allows AXA to operate not as a distant vendor, but as a true extension of the client's engineering team. This people-focused approach is reinforced by a highly stable workforce. With a 97% employee satisfaction rate, AXA retains a team of professionals who are not only technically proficient, but also committed to long-term project success. High retention ensures knowledge continuity and dependable delivery, key strengths for multi-phase, complex engineering work. AXA's operational rigor is matched by its use of advanced technology. Tools like Autodesk Civil 3D and InfraWorks are employed to turn raw geotechnical inputs into detailed three-dimensional subsurface models. Borings, CPTs, and test pits become part of an interactive digital twin that visualizes soil layers, groundwater conditions, and geotechnical properties in spatial context. These models allow engineers to assess how foundation options interact with specific soil conditions and to identify weak zones or settlement risks before construction. This level of predictive analysis goes far beyond traditional two-dimensional reports, improving safety, reducing costs, and supporting better design decisions. What defines the AXA difference is the integration of rigorous quality control, direct cultural immersion, and advanced technology. By embedding engineers into client workflows and leveraging data-driven modeling tools, AXA transforms geotechnical interpretation from a preliminary task into a strategic advantage. It eliminates common outsourcing risks such as miscommunication or poor context while maximizing the value of global collaboration. For design firms, partnering with AXA means working with a team that is technically strong, context-aware, and fully invested in delivering high-quality, reliable engineering insights. The conclusion of any civil engineering project depends on decisions made long before construction begins. A geotechnical investigation is not a discretionary expense. It is a critical investment in risk management and project certainty. The real value lies in the methodical process of translating complex site data into clear, actionable recommendations. Partnering with a firm like AXA Engineers, which combines rigorous methodology with technological innovation, ensures the story told by the ground is one of stability. This strategic alignment safeguards the project, its budget, and the firm's professional reputation.